Okay, so this is an introduction, and the objectives of this introductory lecture actually are the following. First, we're going to start with getting what is number theory. Unlike other courses in mathematics that you have taken, usually it is hard to give a definition for the subject or for the course because it uses some terms that you are probably unfamiliar with. Unlike that, we're going to see we will be able to give a definition of what number theory is using familiar terms, and the definition will convey what actually this course is all about. Then we move into give a list of some number theoretic problems. Some of these problems are solved, and actually we will go over the proofs or their solutions. And there are some which are unsolved, means they are still open problems. And we're going to see also, unlike other classes in mathematics, you will understand what the problem is asking and probably will make an attempt to actually try to prove it, okay? What property or whatever the problem is stating. Then we're going to give a short axiomatic approach to the natural number system. And we're going to see that with this, we can, all other number systems, such as the integers, the rational numbers, the real numbers, complex number, actually can be constructed, all right, using a few axioms. There's a total of 5. And we can build the whole number system, as you know it, all right, from these 5 axioms. And then we're going to define, all right, the arithmetic operations of addition and multiplication. And of course, you can extend that to define subtraction and division, all right? And then we're going to finally prove some properties of these 2 operations. All right, so let me get started with answering the question, what is number theory? All right. So as a first attempt at the definition of what number theory is, I'd say the following. Number theory or sometimes it's called higher arithmetic. Is concerned at least in its elementary parts by the study of the set of integers that we denote by the letter Z, consisting of 0, plus minus 1, plus minus 2, and so on, under the arithmetic, the 4 arithmetic operations, which is addition, multiplication, and their inverses, which is subtraction and division. Their inverses. Of course, the idea here is to study different sorts of numbers, all right, among the integers. We're going to classify basically they have different classification for integers. All right, probably you are familiar with positive, negative, and zero, and then you have the even and odd. Then we have some other types of classification, so we would like to look at those, and then we're gonna actually try to prove some general properties or relationship among these different types of numbers. In particular, our emphasis will be actually in the set of natural numbers more, but to make our study easier, we're going to allow also to deal with and work with negative natural numbers, which we call it the negative integers. All right. Now let me go to the second objective. As you see in here, just before we move on, I say it's elementary parts. All right. In other words, number theory is a very, very wide and very big actually area in number theory or in mathematics. The type of number theory that we're going to study is called elementary number theory. And the word elementary here is actually used in the technical sense. It doesn't mean that it is an easy, area. However, it's simply the word elementary convey or means that we only use, all right, we don't use, basically, that's probably a better way to say it, we don't use the theory of functions of complex variables and analysis actually to study number theory, or use which is called analytical techniques. And this is the branch of number theory which uses that. It's called analytic number theory. And then there is another branch which we call algebraic number theory, which we use the apparatus of algebra, this heavy algebra. Here we're going to be using just something very, very basic as far as the approach or what elementary number theory means. All right, doesn't mean simple. All right, it just means that the tools that we are used are basically the tools of arithmetic that you are familiar with, and of course we're going to develop some other ideas along the way. All right. So let me start with the second question, which was to give a list of some number theoretic problems. So let me start with the first. Okay, so here's a list of number theoretic problems. Alright, first one is this: is the sum of two square natural numbers is a square. The sum of two natural numbers itself is a square. Of course, we know the answer to this, I hope. The answer is yes. For example, if you take a 3 squared plus 4 squared, as all this is 5 squared. We also have 5 squared plus 12 squared equals 13 squared. And these two examples are 2 out of infinitely many. In fact, there are infinitely many natural numbers A, B, and C such that A squared plus B squared equal C squared. Such order triple, when you write it like this, A, B, C, is called a Pythagorean triple. A Pythagorean I don't know why, triple. All right, so we all know this, okay? And if time allows, this is actually presented at the very last chapter of the book. If time allows, we will be actually able to tackle this problem, means find all the Pythagorean triples, okay? Describe them. Means we cannot list them, they are an infinitely many. All right? Then another related question to this, how about if we want to take the sum of two cubes? So, is the sum of two cube or sum of two cube natural numbers is a cube? Let me write this down. Okay, the sum of two cube natural number is a cube. Or how about sum of 2/4 half numbers? Again, the word numbers in here means natural number unless it's stated otherwise. Is a fourth half of a number. And in general, one may ask, is the, let me put here is, all right, is the, let me put a question mark here, and in general, is the sum of 2nth power of numbers is an nth power. Of a number. The answer to all of these is no. In fact, if we translate this into the language of mathematics, algebra, arithmetic, there's what it says is x squared plus y squared, cube. We have this one is true, of course, for the square, is this equal z to the third for some x, y, z. These are natural numbers. Set of natural numbers we denote by n. Let's start from 1 to and so on. Or fourth power, or in general, is this. All right. Does these equations, basically, if you think of this equation as in three variables, does this equation has solution, and the solution are natural numbers? Okay, such type of equation called Diophantine equation, and we're going to be studying some of this. It was conjectured, all right, by Fermat In fact, Fermat stated it as a theorem, all right, in the 17th century, that yes, there is no solution for this. There is no two integers that you take their cubes and add them and you come up with the cube of another integer, all right, or to that matter, nth powers for n bigger than or equal to 3. The theorem that Fermat stated, and has an interesting history you might be familiar with, the way he actually made this statement on a margin of a textbook, and he said that, not a textbook actually, of a book he was reading by the Fontinus of Alexandria, and he said that he has a marvelous proof for this theorem, or for this fact, but the margin of the book is short enough not to be able to write it down. All right? The theorem, since then, it is known as Fermat last theorem. All right? So we're talking about in the 17th century, 1600s, Fermat last theorem, that's what it's called, which says that the equation x to the n plus y to the n equals z to the n for n bigger than or equal to 3 has no integer or integral solutions. It took many generations of mathematicians to try to actually solve this problem, and there was a prize actually set on it. What is equivalent now, the price back in the early 1800s, 1900s, all right, for almost $1 million, what it's worth now. And it was solved only in 1994 by Andrew Weil. And the proof that actually Andrew Weil presented consisted of hundreds of pages, and it with heavy, very sophisticated mathematics, all right, and several pages of proof. And initially, actually, when Andrew Weil announced the solution for Fermat last theorem, everybody was excited, and it turned out that he has some gaps in the proof itself. So it took him another 2 years with help from his friends, actually colleagues and students, and the result was published in the Annals of Mathematics in 1994. All right. So as you can see now, how long it took to solve one problem. It's very easy to state, as you can see. Anyone can understand what the theorem is saying and what is required to do to solve. Okay. How? That's the big question, which sometimes, as you can see, it's not easy to answer. Or to talk this much. There are many generations of mathematics actually contributed to the final result that Andrew Weil actually were able to put together to come up with a proof of Fermat last theorem. All right, so this is solved, unfortunately, but I will have a few more problems that are not solved, which you can become very famous overnight if you can solve any of these problems. The next problem is the following. As you know, I need a definition. A natural number p bigger than 1 is called a prime number if the only factors or divisors of P are 1 and P itself. We know that, okay, so you know what a prime number is. Here are several questions we can ask. Are there infinitely many prime numbers? So this is another classification of the natural numbers usually, okay? A number is a prime, or if it's not a prime, we call it composite. And if it is 1, we call it 1, so which is neither a prime or composite. The answer to this, yes, and it was proved by Euclid in his Elements. And we're going to actually go over Euclid's proof. There are many other proofs given since then. But the nicest one is actually Euclid's proof of there are infinitely many primes. Also, one might ask, are there infinitely many primes of this form, of the form 4k plus 1, where k is equal 1, 2, 3, and so on. All right? Actually, even we can start with 0k. Let me explain this a little bit, what I mean by this. So these are numbers which are a multiple of 4 plus 1. So in other words, these are the numbers which leave a remainder of 1 when divided by 4. Another name for these, because these numbers are 1 mod 4. It is something that we will be studying in this course. Now, not all the numbers of this form are primes. For example, when we put k equals 0, we get 1. This is not a prime. When k equals 1, this gives you 5. It's a prime. When k is equal to 2, this gives you 9. 9 is not a prime. And so, it turns out that some of these numbers are prime, some are not. And the question is, are there infinitely many primes in this? Actually, this is an example of a, it's called arithmetic progression, or a sequence, arithmetic sequence. The answer is yes. Okay? And again, we're going to prove this. Another question, how about primes of this form? 4k plus 3. In other words, those numbers which are 3 mod 4. And the answer is yes. Because the other numbers which are similar to these, or of these forms, is 2 mod 4, but these are not all of them. They have a multiple of 2 or 4k, all right, or 4 mod 4, and these are multiples of 4, and these are, none of them is a prime. All right, and again, we're going to see proofs of this. There is a generalization of these type of questions, all right, looking at the primes of a certain form. As I say, this is called arithmetic progression or arithmetic sequence. The 4k plus 3, it starts with 3 and then you keep adding, 4 to it. Okay, so if you want to list, for example, either one of these, it starts with 1, then 5, then 9, you would keep adding, 4 and so on. So this is called arithmetic sequence or arithmetic progression with a common difference 4. Okay, and similarly you can do that one. The German mathematician Dirichlet generalized this to the following theorem, and it's proved, of course. All right, so these become, of course, just the special cases. All right, Dirichlet. Please look at the spelling of this. Dirichlet with, let's see here. I murdered this, there is an I in here. Okay, Dirichlet. All right, this is an I. In 1837, all right, he said the following theorem, says that let A be to be natural number such that the greatest common divisor of A and B is equal to 1, means they are relatively prime. A and B are relatively prime. Then there are infinitely many primes in the sequence, in the arithmetic sequence, which is A plus bk, where k is equal 0, 1, 2, 3, and so on. All right. So this is again the generalization of those primes of the 4k plus 1 or 4k plus 1. The proof of Dirichlet theorem, all right, is very, very involved. Means it's not a simple proof. So we're not going to be able to actually do anything with it. It's a nice, actually, result. All right, let's look at a little more type of problems, which is similar to the very first problem that I stated, which has to do with the sums of squares and cubes and so on. This is number, I don't know, 4. Which natural numbers are sum of 2 squares? All right. So it's not very hard to experiment with some numbers and being able to write those numbers as sum of 2 squares. The question here is asking to give of course, a generalization of this, not just to come up with a specific example, to give a description, what type, what sort of numbers which you can express as a sum of 2 squares. And we're not here saying that the 2 numbers which you have to square has to be different. They could be repeated. All right, and sometimes we can write a number as a sum of 2 squares with more than one way. And then another question would be in how many ways this can be done, and so on. All right, the problems like this sometimes you could approach by looking at, consider the primes. Consider this problem for prime numbers. in fact, the one advantage of number theory is you could do some experimentation, okay? You could do some guessing and try to look at a few cases and see if you could generalize this. So for example, if I take 2, yes, 2 is a sum of 2 squared, 1 and 1. Is 3? No. You cannot write a 3 as a sum of 2 squared. But we're going to consider it as just a prime number. We're going to concentrate on the primes here. The next prime is 5. And 5, yes, you can write as 2 squared plus 1. 7. Let's see, 7. Can we write 7 as sum of 2 squared? No. So this is no. And by making a list, okay, actually the next prime number is 11, and you're going to see that 11 is also no. Maybe let's one for a couple of more in here. 13, yes, which you can write as 2 squared plus 3 squared. All right, and one more, let me put one more, 17. It turns out, again, yes, and you can do this one, 1 squared plus 4 squared. And you might try to do this one in maybe, different ways. Let's see, any one of these can we do in different ways. No, you could try. So it looks like, yeah, there are some we can do, some we can't. Okay. And by looking at this, sometimes you want to try to see what kind of primes can be written as actually a sum of 2 squared. It turns out that primes of this form. Okay, if P is a prime and is equal 4k plus 1 for some k, a natural number, then yes. Then the other type of primes, so this is yes for this, and if you check the one which we did in here, but this is not a proof, it's an observation, of course. And then if P of the form 4k plus 3, no. We cannot express any prime like this. And then from there, you would like to, of course, to classify all numbers, not just the prime ones. A similar question to this, maybe instead of asking which number are sum of 2 squared, 2 cubes. And it turns out, yes, there is a classification for this, and actually this is what was studied by Gauss, all right? And he gave a number of ways we can do this, okay? This is a little more hard. Again, this material is presented again toward the end of the textbook, and I don't know if we will have a time to get there or not. On the other hand, so in other words, there are some numbers can be written as sum of 2 squares, and there are some numbers cannot. And similarly for cubes. If we ask for the next power, which is the sum of 2, actually, sorry, I want to say this one is the sum of, instead of 2 over 3 squares, over 3 squares. Not the cubes, I'm sorry. At least this is the problem was worked by Gauss. And again, there are some numbers can be written as a sum of the 3 squares, and some they cannot be. Another question is, which natural numbers can be written as a sum of 4 squares? 4 squares. Lagrange in the 1700s, late 1700s, 1800s, proved every natural number is the sum of 4 squares. Any natural number can be written as a sum of 4 squares. All right? All. And again, this is already solved. Okay? Next we look at some other problems. See, these are interesting. They're very easy just to convey, the nature of the subject, but number 3 is all about, and the type of questions that we're going to be working with. All right, how easy to describe, and hopefully easy to understand the proofs. Okay. As you all know, we can classify numbers as square numbers. We have square number. And these are 1, 4, which is the square of basically the eraser, right? 1, 2 square, 3 equal 4, then 3 square, 9, and so on. And these numbers we can represent by using dots on the board or a piece of paper. And we call these figure numbers. Okay, so we can think of square numbers as figure numbers. In this sense, we represent each number by dots to make up a square. For 1, of course, we just have the generic kind of square. And then 4, we make a square. And for 9, see 1, 2, 3, 1, 2, 3. So we have 9 dots, and so on. So equal, the square numbers, they are figure numbers which can be represented geometrically like this. Then the next type of numbers, we call them triangular numbers. And these way you can put to make an equilateral triangle. Okay? So the triangular numbers, we denote them by T sub n. All right, and these, for example, when n equal 1, we have just 1 dot, and then the next one, we need actually 3. So this is equal to 3. And we call this is T2. So this is T1, this is T2, because we need the second one. And then the next one is going to be, we need a triangle, so we need to make the base consisting of a 3. Then the next level, we need 2 points, and then 1. All right? All these are equidistant from each other. So this number, as you can see, it consists of 3, 5, 6. All right? And so you could keep going. The question is it possible for a natural number to be both a square number and a triangular number? Well, again, by experimentation, if you keep listing these numbers, all right, the triangular numbers and so on, the answer is yes. Yes. The smallest natural number that is both square, a square number, a square and a triangular number we say actually a square number and a number is 36, which I know this is 6 squared. And the triangular number that actually will be the 36 coming from these, that's the 8. Actually, not the 8, let me see in here. Is it? Yeah, it's the 8th number actually. 1, 2, 3, so on. So if you add these, you come up with 36. All right? Then the question is, are there many others? Are there others? Other numbers that are both the square and the triangle? Of course, the answer is yes. And the question is, can we classify these? Can we tell when a number is both a triangular number and a square number? Of course, as you can see from here, we have a formula for the sum. In other words, the T sub n is equal 1 plus 2 plus 3. This is the triangle number. We start with 1, and then we need to add 2 points, and then we add the 3, and so on. This is the way we form these triangular numbers up to n. And we know this is n plus 1 over 2. And the question is it possible to have this as equal m squared for some m in an actual number? So this is what actually answering this question amounts to. All right, let's move on to a little more with some unsolved problems. Okay. Now, if we look at the list of prime numbers, which is an infinite class, and examine, some relationship among these primes. So if I start with the smallest prime is 2, then we have the 3, then we have 5, we have 7, and the next one is 11 and 13, and so on. I want to go very far. Now, sometimes you see these two are primes, and they are consecutive odds. Okay, 3, the next consecutive number that is odd to 3 is 5. These are consecutive. From 7 to 11, no, they are not next to each other as far as being even odd. 11, 13, yes, these are. So prime numbers like these, we call them twin primes. So what's a twin primes means? All right, twin prime is P and it's an odd, all right? A twin prime consists of a prime number, an odd prime number, because the 2 is the only, even prime of the odd, of an odd number, an odd prime number, P, and P plus 2, that is a prime as well. Two such numbers where P plus 2, these are primes, we call such two primes, we call these are twin primes. So these are called twin primes. Now it's not very hard to move on to the sequence, and you're going to see there's, these occurs in different places. Actually, then the question becomes, Degeneracy there will become, rare, means little less their occurrences, but still they come. And the question is, are there infinitely many? Infinitely many? It will the process. Or only finitely many, and then the next thing is to list them. Up till now, this is an open problem. Okay? This is unsolved. Again, a very well-known problem for many, many, many years, centuries, okay? Simple to describe, but nobody knows what the answer is. All right? One other thing one might ask about, how about triplets? Means, or triple primes, or sometimes called the triplets. All right? So you would imagine, if you want to try to mimic this definition, that if there are 3 prime numbers that are next to each other, then you would call that a triplet. Well, in fact, the 2 here is not going to work, but you can say that the 3, 5, 7, okay, this is a triplet. All right? They differ by 2. In other words, they are next to each other as odd numbers. Okay? And they happen to be, of course, all primes. So a triplet consisting of 3 consecutive, let me write it down. So, a triple prime consists of 3 consecutive primes. So they're going to look like this. P, it's a prime, P plus 2, and P plus 4. The question is, are there infinitely many triple primes? Are there infinitely many triple primes? The answer is no. In fact, the answer there is only one. Only one. Only one. One triple prime. And that is the 3, 5, 7. 3, 5, and 7. In fact, let's see how we can prove this. Okay? Because the proof is so simple, it doesn't need very much, techniques or any sophisticated theorems or results needed. It's very basic. Well, let's assume that P plus 2, P plus 4 is a prime triple, or is a triple or triplet prime. And we're going to assume, because we wanted other than the 3, 5, 7, and or where P is bigger than 3. All right? So this means that, of course, B, first of all, because it's subprime, it cannot be a multiple of a 3. So P does not equal 3K or any K. But it can be a 3K plus 1. B may have the form P equal to 3K plus 1 for some, because it's bigger than a 3, so it's gonna, the smallest number bigger than 3 is actually, which is 4, of course, and 5, and 6, so of course the multiples of the 3 can be, okay? So this one, he cannot, because it's not a prime. Okay, so the next thing is we have this 4 for some K to being a natural number. It means bigger than or actually equal to 1. All right? Well, in this case, then, P plus 2, let's look at what that's going to be equal to. 3K plus 1 plus 2, and this becomes a multiple of a 3. No. So any prime, that's what this one is saying, of this 4, the 3K plus 1, would make the prime next to it actually being not a prime. This is a multiple of a 3. Or, another possibility, for P may equal to P is 3K plus 2. So you can classify the natural numbers into multiples of a 3, or multiples of 3 plus 1, or multiples of 3 plus 2. These are called actually the integers bar 3, which we're going to introduce this to test. But it's very easy to kind of understand this classification. We know that the even odds, for example, are multiple of 2 or multiple of 2 plus 1, right? And we could do this for 3 and 4. We're going to have, of course, more classes. So for this, if the prime has this form, then P plus 4, which is the next one, it's going to be the 3K plus 6. And again, this is a multiple of the 3. Again, it can't be. So the only prime triple or triple prime is the 3, 5, 7, because any other will not work. So two similar problems. One of them, nobody knows what the answer is. One is simple to actually solve it and determine exactly what it is. All right, I want to list 2 more problems. And both of these unsolved. And here it is. When I consider primes of the form 10 squared plus 1, where 10 is a natural number. The question is, are there infinitely many? Many primes of this form, of the form n squared plus 1, or n equal 1, 2, 3, and so on. Again, not every number of this form, when n ranges over all the natural numbers, is going to give us a prime. Some of these will be prime, some of them are not a prime. So for example, if I start with n equal 1, this is equal to, yes. How about 2 squared? Yes. How about 3 squared? So one is going to be 10. Of course, no. We continue a little more. 3 squared, 4 squared, plus 1 is 17, yes. 5 squared plus 1 is 26. No. In fact, it's not very hard to see if n is odd, n squared plus 1 is even, which means it's not a problem. So to answer this question, we're going to be basically wasting our time if we want to consider, n to be odd and square it and add 1. So maybe we only need to concentrate on the even ones. So the question becomes, are there infinitely many primes of this form where n is even? N belongs to 2, 4, 6, and so on. Or in general, 2k. Again, turns out this is an open problem. This is unsolved. And of course, with the computer, people try to answer questions like this for very, very, very large values of n. And so far, they get actually primes. Okay? And then they get no primes. All right? The last problem in this list is called Goldbach conjecture. The conjecture means it is not a theorem. It means nobody knows if the statement is true or it is false. All right? And again, it's been around for the same about as Fermat's theorem. So this is called Goldbach conjecture. And it was proposed by Goldbach in 1742. And it says that every even natural number is the sum of 2 primes. Two prime numbers. Of course, we have to do repetition, that's fine, but that's what this is saying. So if you look at actually every even natural number bigger than 2. Okay, bigger than or equal 4 is from 2 on. 2 because it doesn't work, right? Is the sum of 2 prime numbers. So if you go with 4, which is 2 plus 2, and then the next one is 6, which you can write as 3 plus 3, so prime. The next one is 8, 3 plus 5, in 10, 3 plus 7. Let me go one more, 100. I don't know if I have 100 here. It turns out to be 29 plus 71. Now, user computers, they have checked the validity of this conjecture for numbers, for even natural numbers, which have hundreds of digits. Very, very big natural numbers. Numbers without name. Okay? And turns out, yes, it is true that each one of those is the sum of two primes. But even with these large values of n and checking them to be true, does not validate this conjecture. And no mathematical proof, all right, actually, as it's no. So this is again an unsolved problem. It's open problem. All right. It doesn't mean that there is nobody who is trying. No, there are many attempts made to prove these unsolved problems, but no final solution has been actually given. And there are some other problems which remain unsolved, all right, for hundreds of years, and recently, actually, they are solved. Another problem along these lines is called the Catlin conjecture. It was just solved. Catlin proposed this in the 1800s, and it was only solved in 2002. Okay? So, as you can see from this list of questions and what number theory is, it looks like it's something easy to understand, and there is no terms that you are unfamiliar with, at least in the description for these problems. And we're going to see throughout the course, a lot of the vocabulary that we use is very familiar, okay? And once in a while, we introduce something you have not seen before, means some new concepts, all right? Well, unfortunately, I'm going to stop right here. It took a little more time than what I thought. And for in the next lecture, I'm going to be talking about the axiomatic approach to the natural number system, all right, and introduce actually the axioms needed to build up the set of all natural numbers, and then being able to define addition and multiplication, and at the same time prove some properties of addition and multiplication, such as addition is commutative, distributive property, associative, and so on. All right? So I'm going to stop right here.